Good morning, everybody. How we doing? Good. Except for the fact that there's a test next week? Yeah? Yeah? What'd you guys do with the rest of the class? Just everybody. Crazy. Good news is that we're about to do one chapter in one day, which is sounds scary, but actually isn't, because we're actually just going to do what we've done before, which is DC circuits. Don't do that section. And I don't think your book does this, but if you run across AC circuits in any other context, like YouTube, online, whatever, ChatGPT starts telling you about phasors, just ignore it, okay? A phasor, spelled with an O, is a rotating vector, and vectors are bad enough. We don't need to put them in rotation. So, and they're not, unless you're going into electrical engineering, there's absolutely no reason to be thinking about it. So just we're gonna make this a one-day chapter by tossing some information out that we don't have to worry about. Okay, so we are going to. Cheat's a strong word here. Okay, because what we're going to do is, yes, we're going to cheat. However, it's not a physics like 2B cheat. Like it's not like, oh, we're going to make this easier and pretend. No, this is exactly what everybody does. Electrical engineers do this. All of our electrical grid and everything that we've defined does exactly what I'm about to show you. Okay. Part of the problem in dealing with alternating current circuits, as we saw last time in my demonstration at the end of class with that generator and that flickering light bulb, whenever Faraday's law of electromagnetic induction is generating electrical current, naturally, because you need that change in flux, there's going to be this alternation. And quite frankly, what we have to do is we have to think about the voltage and the current as sine or cosine functions, which is already sounding bad enough, right? Okay. But if we were like plot the voltage or the current in time, okay, we get these wiggles. Now, to deal with those wiggles is actually hard. Like we'd have to have time-dependent equations, and as soon as you get time into it, What we do know how to do already is DC currents, direct current circuits, where the current just flows in one direction. We know Ohm's law, we know resistance. We can do series and parallel, all that kind of stuff. So what we do in AC circuits to simplify the everyday mathematics is we ignore the fact that it's wiggling and we pretend like it's a DC circuit. Now, this is cheating a little bit because we're ignoring some very fundamental physics in that it's wiggling. And it's a cheat in the sense that we've got to introduce a little bit of statistics in order to make this happen. Okay, what do I mean by that? A sine or a cosine function, like what's its average? Like if we take a look at this voltage over time, right? One way to kind of get rid of wiggles or anything like that is to take averages. But what happens if you take the average of a sine function? It's 0, right? It spends just as much time above as it does below the horizontal axis. And so when you take that all into account, you do all pluses and minuses together, you get 0. So the average isn't very useful. So we got to reach for a little bit more statistics, which is why you're going to see something called the root mean square value, or RMS value, used quite often in the textbook and in my, as I write stuff on the screen. What is a root mean square? Well, okay, so you know what a square root is. The mean is an average, and of course we're squaring something. So to get around this problem that the average of this function is 0, we're going to take every part of the population, all the numbers that we've got, all the currents and voltages in our circuits, okay? And what we're going to do is we're going to square it. Now, squaring something that does both positive and negative gets rid of the negative, doesn't it? Right? So like if we square this sine function, this downy part becomes goes up like that, up, right, up. And then it inflates it all, right? by the square, right? Not only does it make it positive, but it also increases it. Then we take the average of that, okay? And now because we've introduced a square factor, when we're done taking the average, we'll take a square root. This is called the root mean squared, okay? Now, the good news is we don't actually have to calculate this, okay? But everything I'm about to show you is based on this idea that we're going to wink, wink, we know it's AC, but we're going to treat it as a DC circuit. And this is about to get kind of weird, okay? Because I'm about to tell you that capacitors and inductors are going to have resistance. In an AC circuit, we actually treat those things as resistors. In DC circuits, we made sure that we knew the difference between a resistor and a capacitor. Capacitor stores stuff, right? A resistor uses up electrical energy. Well, it turns out in an AC circuit, a capacitor can do both of those things. It can store, but it can also use up energy. Same thing goes for an inductor, which is a solenoid in a circuit. So I'm about to kind of just lay out, right, this big cheat, okay? And see where it takes us. Okay, so what I kind of want to do is maybe do a little bit of compare and contrast between what we had in DC circuits and what we're going to be doing for AC circuits. So in DC circuits, there was like a key rule that all things in a circuit obeyed, and it was Ohm's law. Do you remember what Ohm's law looked like? Voltage equals current times resistance, something like that, right? Okay. Well, in AC, okay, that would be VRMS equals IRMS times something new that we're going to call the impedance. Okay. Now, I'll get more into impedance in a minute, okay? But impedance is a way of finding the equivalent resistance of the circuit. When we were in DC circuits, we had parallel and series rules, right? If we had parallel capacitors, we had to add their inverses. If we had parallel resistors, we had to add their inverses. And if we had series resistors, we had to just add them up. We were able to take these complicated circuits and mush them down. It's a lot more complicated in AC, which is why we're only going to do one kind of circuit, and that's the series circuit. But I'm getting a little bit ahead of myself, okay? Now, do you remember power? Power was it current times voltage? Pretty sure, okay? In DC. In AC, the average power, again, we can't really talk about an instantaneous in-time thing, okay? Because this stuff changes in time, and we kind of want to ignore this changing in time thing. So we'll just talk about the average. Turns out to be the RMS current times the RMS volt. I mean, so far so good, right? We're just kind of throwing RMS on stuff and then changing a few of the symbols. Only this is where it really starts going bad. Times the cosine of phi. Where the cosine of phi is equal to the resistance in a circuit divided by its impedance. My advice right here is just go with the flow, okay? I'm not sure that there is any benefit to understanding what's going on under the hood of an AC circuit. There just really isn't. There's benefit in understanding why we have to deal with it. Faraday's law generators, they generate alternating current. But then how do we deal with it? We pretend it's a DC circuit, and that gets us 98% of the way where we need to be. And the other 2% the electrical engineers can deal with, okay? All right. What else? Oh, the other way to find phi is to do the tangent. Well, I'll get to that. You know what? Let's wait on that one. Let's wait on that one. Okay. So, yeah.
What's under the R?
Z. Looks like a Z to me. It's a Z, but my Z's and my 2's look the same.
Okay.
And so I was taught by somebody somewhere to just put a bar through my z's. So this thing right here is also a z, right? So we'll just be. See, it just doesn't work. No matter what I do, it doesn't work. So anyway, those are z's. Okay. All right. Okay, so there's some other things. This right here, by the way, is often called the power factor for a AC circuit. If you're ever asked to find the power factor, just find the cosine of the angle, or just take the resistance divided by the impedance. Again, we'll get to impedance here in a second. Okay, so one thing you need to understand about RMS, like root mean square, okay, is that there's a difference between this root mean square, which is like an average, and then the maximum voltage or current that could be happening anywhere in the circuit. Okay, and so the conversion between like the absolute most you could have and the time average is a square root of 2. And this applies to the current as well. RMS current is equal to maximum current divided by the square root of 2. So what does this mean? In AC circuits, so like the wall outlets right here, the ones in the tables, okay? By standard, okay, they're supposed to be operating at 120 volts. Okay, anywhere between 110 to 120 volts. But that number, like whenever you're talking about AC circuits and you're just told the voltage, like they tell you that a generator produces 120 volts, you always assume it's RMS. Unless you're told otherwise, voltages and currents and everything in AC circuits are root mean square values. So when I say that the wall outlet's 120 volts, I mean RMS, okay? On average, 120 volts. However, that doesn't represent the maximum voltage that could be coming out of that outlet. What would the maximum voltage be coming out of this outlet? Not unlimited.
120.
It's not 120. RMS is 120. The average is 120. But if we solve for the maximum, then we take the square root of 2 up here. Square root of 2 is like 1.7-ish something, okay? And 1.7 times 120 is like 170 something, okay? Can I get my fancy little AI thing to work? Square root of 2 times 120 equals. Oh. Solve 170. Okay? So, this is what happens when you write clearly, I guess, right? So it was 170 volts. That means that actually the outlet can do 170 volts. It just does that once every 60 times a second, because here in the United States, the frequency at which we generate electrical power is 60 hertz, okay? So 60 times a second, our electrical power goes through one of these full sine wave wiggles, okay? Now in a sine function, right, you have a peak and a trough, right? So this peak right here is a max. This other peak, you could think of it as a min, but it's just a negative max, okay? So that means in 1/60th of a second, it's got to go through the whole thing, which means 2 times in that cycle, it's reaching that 170 or negative 170, right? So I guess, but there's also 2 times where it's 0, right? Okay. Now, I don't advocate this kind of thing, but this sounds like a new game. A little bit like Russian roulette. And if you're fast enough and you time it just right, it could be 0. Yeah, no, don't do that. No, don't do that. Can't do that. Can't do that. But the point is, right, that AC is fluctuating all the time, right? And this root mean square or RMS value is a way of capturing the average value that's there at any moment, right? And all of our electrical circuits, all of our devices, everything, that's what they are expecting. Okay, so let me show you I want to show you a simulation of kind of what's going on here. And maybe it'll help, maybe it won't, okay? But in this simulation I've got here, okay, we have this wiggle. And we're doing AC because the battery, the voltage source, instead of being the battery symbol, will be a circle with a squiggle in it, okay? A sine wave, meaning it's alternating, okay? So here we've hooked up an AC generator to a resistor, okay? And what the simulation is going to show us is the voltage across this resistor. And if we let the simulation run, okay, we would see that the voltage through that resistor is changing in time, as we expect, right? But we kind of average all that out. We do that root mean square thing, the average of things that are zeroed, all that kind of stuff. So here's the problem, right? If we add a capacitor to our simulation now, okay, we've changed the circuit, true. What kind of circuit is it? Series or parallel? Series. Generator, resistor, capacitor, back to generator. There are no branches, right? Okay. So this is a series circuit, right? Notice when we added this capacitor in series, in the AC version, do you see how those two curves are offset? And they're not happening at the same time, okay? So again, if we play our thing there, right, and we try to measure what's going on in the circuit, the capacitor and the resistor are doing different voltages at different times. I don't want to get into why. I'm just pointing out that this is what happens. Okay, now we add an inductor, which is a solenoid, into the circuit, okay? And so again, it's still just a series circuit, isn't it? We haven't added any junctions here, okay? Now that the inductor's in place, we got a third wiggle. And my brain fried just on one wiggle, but now there's three. And like keeping track of what's going on at any given point or any specific time in the circuit becomes really hard. And thankfully isn't necessary except for some very specific applications that we normal human beings don't run into on a daily basis. The upshot of all of this is that even though this is going on, we can ignore it if all we want to do is apply or be able to figure out what's going on in an AC circuit in a simple manner. So let's talk about the series RLC circuit. So series tells you what? How many junctions will there be in any of these circuits? 0, right? No matter what happens, there will be no junctions, okay? RLC, what does the symbol R mean? What does the symbol C mean? Capacitance, okay? And then the L is the symbol for inductance, which is a property of a solenoid in a circuit. Okay, so why are we talking about series RLC circuit? This will be the only circuit we do. This is a physics 2B thing, okay? Because we're not going to do the parallel versions of these circuits. And maybe I'll show you why in a little bit, okay? So along with what we had here, okay? So let's copy over. I'm going to grab, I know you can't really see what I'm doing. Let's see, I'm going to grab this. You're going to let me copy that? Copy. Paste. Okay, so along with this stuff for AC circuits that we had before, okay, specifically to the series circuit, the impedance, which I mentioned before, it gets ugly, but don't panic. It's going to be the square root, big square root, of the resistance squared plus two symbols, x sub L minus x sub C, and then that difference becomes squared. I will explain this in a moment, okay? It's enough to understand right now that you need the impedance for what? We need it to be able to do Ohm's law, right? Ohm's law usually has resistance in it, okay? But in AC circuits, it has impedance in it, okay? We need the impedance to be able to figure out the power factor, so on and so forth, okay? So again, I'll explain kind of what impedance is. Let me just get the toolbox down, okay? Then there's these other two symbols, X sub L, okay? X sub L, according to your book, is 2 pi times the frequency times the inductance. And X sub C is equal to 2 pi f times, that is not right. My note cannot be correct. It's 1 over that. Sorry, I was writing. It's 1 over 2 pi f times the capacitance. There we go. That's correct. Okay, what the heck is going on here? A series RLC circuit has a generator, has a resistor, has an inductor, has a capacitor. The actual order of those three doesn't make any difference. You could have the inductor first, okay, after the generator. Like, it doesn't matter where you put them in the circuit. The only thing that matters is that they are hooked up in series with each other, okay? And so we have our resistor, we have our inductor, we have our capacitor. What we're going to do is, instead of thinking about all the physics that goes into the solenoid and the magnetic fields that are going on and all that kind of stuff, we're going to pretend that the solenoid is a resistor. It's just, come with me to the dream make-believe world of AC circuits. Like what I'm about to tell you is the easy way, okay? Because the real way is the hard way, and we don't want to go there, right? So as sort of weird and maybe complicated and convoluted as this explanation's about to get, this really is the easier way to deal with it, and it is what all electricians do, right? Anybody that works in AC does this because doing the real deal is that bad, okay? So this X sub L right here, okay, that's referred to the inductive reactance. Reactance is a fancy word meaning we've turned this thing into a resistor, okay? So we've got inductive reactance and we've got capacitive reactance right there. One's associated with the inductor, one's associated with the capacitor. Now, since we're using like X sub L and X sub C, right? Do you see how we're subtracting them from each other and then adding them to resistance in our impedance? What must the units of XL and XC be? Has to be ohms. Why does it have to be ohms? Because you have to add apples to apples, right? The units have to be the same here, right? So that means the impedance, which again is acting like the equivalent resistance. That nasty square root there is hiding a lot of math that is very different from our series and parallel rules that we had before. Like series resistors, we just add them up, right? Well, it turns out we can't cheat that badly in AC circuits, okay? When you have a circuit, so in reality, if we were to do this in parallel or to start mixing series and parallel together, for every circuit, you actually have to rederive the impedance. The impedance is unique for every AC circuit. And so we're not doing that. We are only doing series, and I'm not showing you how we got that impedance. Trust me, you just want to believe it and move on with your life, okay? Don't go down the rabbit hole, okay? All right, So this has units of ohms, right? This has units of ohms. This has units of ohms, right? VRMS has units of volts, because it's a voltage. IRMS has units of amps, because it's current, right? All of that stays. That's nice, okay? You notice a lot of 2 pi. Oh, by the way, your book does this. Other websites do it slightly differently. You might see omega. I know it looks like a W. It's not a W. It's an omega. W's are pokey. Omegas are roundy. Okay. You might see the impedance written as omega L, and I'll make this mistake probably. Okay. Or 1 over omega C. Omega is equal to 2 pi times F. Physicists get lazy. We don't like writing 2 pi all the time. Okay, so we'll often just use omega. And if there's a little tiny piece of your brain that's remembering from 2a, wait a second, I've seen omega before. It was an angular velocity or an angular frequency in simple harmonic motion. Yes, that right there. It's the same thing, right? Because we don't have a mass on a spring. What we've got are charges that are bouncing back and forth in our circuits, right? So their simple harmonic motion is hiding in here. All right, so what else do I need to just kind of warn you about before we get there? Oh, yeah. Another way to find the angle, it's called a phase angle in the circuit, is to take your reactances and subtract them from each other and divide by your resistance, right? So let's see here. We've got power factor. We've got the power in the circuit. We have Ohm's law. We have all 3 of these, which are very, very important, okay? And maybe not so much for our book, but like if you're doing ChatGPT or something and they just throw an omega in there, just remember omega is equal to 2 pi times the frequency, okay? All right, let's, what I want to do is do some examples, right? This represents the toolbox right here, right? These are all the equations we need to be able to handle any kind of AC circuit analysis. Again, let's just standards or the rules that are applied here. If you are told a voltage in a problem and it doesn't tell you anything about that voltage other than the number, what do you assume? RMS, right? Everything, all of these equations get worked in RMS. Now, sometimes problems and physics professors and textbook authors think they're being clever, and they say, well, the maximum output of a generator is 25 volts. Now, did they just tell you the RMS value? No, they told you the maximum value, right? So you have to convert to RMS. So maybe having these in your back pocket just to be able to get back and forth between them might be a good idea. So we work in RMS. We treat the impedance as the equivalent resistance of the circuit. We're going to use the impedance calculation to find the equivalent resistance. And with that, we can figure out everything there is to know about the circuit. And I'm about to do like 3 or 4 examples of just working through different situations in applying this toolbox right here. Okay, so let's start, right, with this problem right here. We're just going to do a little bit of analysis. And again, all physics problems we approach the same way, okay? We need to organize the information that we have. I call this the visualization step, where we're seeing what we've been given. What do the numbers mean? I got to understand it from context, maybe the units that are applied, right? I organize what I have and what I'm looking for, and then I develop a plan in my planning part, and then finally I do it, and then I check it. So what have I been given? 100 hertz. What the heck is that? Of all the things in the boxes on this screen, where does 100 hertz lie? Yeah, it's the frequency, right? Okay, so I'm just gonna call that out. I'm gonna say, okay, I know that it's 100 hertz, right? Okay. Here the problem was really nice and just told us the RMS voltage, okay, is 20 volts. RMS voltage of what? Okay. So it's a generator that has this voltage. It's connected in series to what two things? A resistor and a capacitor. So let's see. We should draw a circuit. And the circuits are pretty easy to draw in this case, right? You just draw a box, okay? And you draw a box, like sometimes I even just draw the box and then I go back and add a resistor. Oops, that meant erase. There we go. I add a resistor, okay? And then I add a capacitor. It looks sloppy. I'll try to do better, right, for you guys. But oftentimes I'll just cheat like that. Okay. Now, does it matter whether you put the capacitor first or not? No. Does it matter if you put the resistor on the bottom or the top or the side? No. It's just they're in series, right? Okay. Just no junctions anywhere, and we won't be doing any AC circuits with junctions in them. Okay. I like to just put pictures, R and C, and the voltage right here. So there's no inductor in this problem, which makes calculating X sub L really easy. What's X sub L going to be? 0. There's no inductor, right? So there's 0 resistance because there's no inductor there. All right, what do they want us to find? RMS current, right? So I'm going to write that down. I want to find the current in this circuit. The things that I have at my disposal for figuring that out, right? There's a current sitting right there. There's a current here in the power equation, but I don't see current anywhere else on the screen. So I don't know the power. They didn't give me any information about power, but they did give me voltage and I'm looking for current. So what's my plan of attack? Find the impedance. Once I've got the impedance, I can solve for the current. Okay? So that's what I'm going to do. And if there's no like RMS specified on the thing, then it's RMS. Okay? Okay, so to find the impedance, I need to do the square root of the resistance squared plus, and then the difference between XL and XC quantity squared. Don't make the mistake of squaring XL or XC and then subtracting. That doesn't work. Right? You got to subtract them first and then square that answer. Okay, to be able to figure out the impedance, I need to know XC, don't I? So what's XC going to be? 1 over 2 pi f times the capacitance. Well, what's the capacitance? It says 0.250 and then microfarads. And you know me well enough now to know what I'm going to insist on, right? For safety purposes. Convert it, right? Don't use micro. Write down 10 to the minus 6. So this is going to be 1 over 2 pi f and then 0.25 times 10 to the minus 6. And throw that in your calculator. I got 6,369 ohms. You can check me if you want. I could have done it wrong. It's an AC circuit. I really don't care. All right, and we know the resistance, right? They told us 10 kilo ohms. And what do we write down for kilo? 10 to the third. Or 10,000 ohms, right? Okay. So now we got our numbers, we can go find our impedance, right? So this is going to be 10 times 10 to the 3 squared plus, and then this is just, I mean, you can put the negative sign in there if you want, 6,369 squared. The negative sign will go away because of the squared. And when I did that, I got 11,856 ohms. That's my impedance. That's my equivalent resistance for this circuit. I don't have to use series and parallel rules. I don't have to worry that a capacitor is a storage device. We're pretending it's a resistor. And Mr. Balogh told me that in a series RLC circuit, the equivalent resistance is called the impedance, and therefore that's just what I'm going to calculate. I'm going to believe it and simplify my life. All right. Now that we know the impedance, what were we looking for? Oh yeah, okay. I should have circled it because I circle the thing I'm looking for. Okay. So now I take my voltage, right, and my current and my impedance. I solve for the current. That's going to be voltage divided by impedance. My voltage was what? 20. And I divide by 11,856. And then I got 0.00169 amps or 1.69 milliamps. Wiley Plus will probably do some annoying thing where instead of letting me type it in amps, it'll want milliamps or picoamps or femtoamps, some weird thing. Okay, take a step back. Was any of the math difficult? No. So what's the hard part?
Organized.
It's just crazy sauce, right? Like, what the heck is going on here? Why am I doing this thing called impedance? Why is everything a resistance? Don't ask why. Normally in physics, we'd be demanding why. Here, don't do that. Because that rabbit hole leads to things like differential equations and insanity. Okay? So just go with the flow. Right? Just accept. Just let it infuse your being. Yes, everything's a resistor. Why not? Okay? It's just a whole lot easier to figure out what's going on if you just do that. Okay? All right, let's tackle another one. Okay? The units of inductance are henries. That's not a joke. Okay? And so we've got a millihenry inductor here. Okay? I do, again, kind of like to start with a picture. I kind of like to know what my circuit looks like. And the pictures are pretty simple, right? Generator. And what are the two things in this circuit? A resistor. I'm going to draw it over here. And an inductor. My resistors and inductors end up looking like each other after a while. Okay? All right. What do they want to know in this problem? Current. Well, we just did this, right? V equals I times Z, which means my current is going to be the voltage divided by the impedance. We know the voltage, right? 20 volts. They gave me the frequency, 60 hertz. Great. Okay. So how do I find the impedance? Big square rooty thing, right? XL minus XC quantity squared. That's supposed to be a C. All right. So that means I have to find what the XL and the XC is. What's XC in this problem? How many capacitors are there? 0. So they have 0 resistance. XL is 2 pi f times my inductance. That's 2 times pi times 60, and then 255 millihenries. What am I going to write for the milli? Does anybody remember what milli is? 10 to the minus 3. Okay, so I calculate that out. I got 96.1 ohms. All right. Do I have enough now to calculate my impedance? Looks like it, right? 525 squared plus, and then it's 96.1 squared. Seriously, arguing with your calculator will be the hardest part. All right? Now that I know what my impedance is, I take my 20 volts, I divide it by 533.7, and that gets me 0.0375 amps, or 37.5 milliamps. Am I going too fast?
Yes.
Yes?
Yeah, I can't write it that way.
Okay, well, it'll be on the PDF, and you can download later.
But it makes sense.
Right? But like, what do you do when you're solving an AC circuit problem?
Just do the math.
Find the impedance, right? Okay. Once you've found the impedance, like you got to figure out all the different parts of the impedance. But once you found it, use Ohm's law in the AC circuit version, and you're kind of there. So let's make this. I don't know if this is a little bit harder, but let's ask some other questions. Okay. Some other possibilities, right? Okay. So this question is a little bit of a twist. Okay. What are they asking us to find here? Find voltage of what? Each element. In other words, find the voltage across the resistor. Find the voltage across the inductor. Find the voltage across the capacitor. Right? That they want to know the nitty-gritties. You remember when we, you probably remember with horror, when we had to take a circuit and kind of munch it down to the simplest circuit, and then we had to unpack that like origami unfolding to get to a specific resistor in the circuit, and it was a nightmare of keeping track of stuff and all that kind of thing, right? Okay. So this is like that same thing, only there isn't really that much unpacking to do, okay? In order to find the voltage across a resistor, well, that's Ohm's law. What do you need to know? If you know the resistance, what else do you need to know in order to find the voltage? Current, right? You need to know the current in that resistor. So what we need to do is we need to find the current in this circuit. If we can find the current that's being delivered in this circuit, and since it's a series circuit, what will the current be in everything? The same, right? The current has to flow through. It can't split up. There's no junctions here, right? So our plan of attack, again, we'll draw our circuit, RLC, okay? So we're going to look for the total current in the circuit. We've done this twice now in two different problems, right? Okay? So we know the voltage, 115 volts, okay, at 60 hertz. This is standard US power supply, okay? We need to find the total impedance of the circuit to be able to find the total current in the circuit. And then, once I have that, I can start answering the question about what's going on in each of the individual circuit elements, the resistor, the inductor, and the capacitor. So let's start. To get impedance, R squared plus L minus C squared, that's supposed to be an L squared. Okay, so let's see here. We know the resistance, 9.9 kilo ohms, so 9.9 times 10 to the 3. Our capacitor, 0.15, and instead of micro, we write down times 10 to the minus 6, right? For the inductor, I should probably put ohms. This is farads. This is 25 millihenries times 10 to the minus 3 henries. It was named after a guy with the last name of Henry. All right. Okay, so now I'm going to go find X sub C and X sub L. X sub C, 1 over 2 pi F times C. So that's 1 over 2 pi 60 times 0.15 times 10 to the minus 6. There we go. I got 17, I'm running out of space over here, 17,683 ohms. All right, X sub L. 2 pi F L, 2 pi 60 times my inductance. What was it? 25 times 10 to the minus 3. And I get an X sub L of 9.425. That's not 9,425, that's 9.4. So compared to the capacitor, is the inductor doing much in this circuit? Hardly anything, right? Like all the resistance seems to be with the resistor and the capacitor. Okay, so now we calculate our impedance. Square root of 9,900, that's 9.9 times 10 to the 3 squared, plus 9.425 minus 17,683. Quantity squared. It seems like a shame to put that all in the calculator when it's such a small difference. This is equal to 20,257 ohms. So now I will go ahead and find my current in the whole circuit. So it's like the total current in the circuit. That's going to be 115 volts, all divided by 20,257 ohms. Gets me 0.0057 amps or 5.7 milliamps. Okay, so we did what we did in all the two example problems we had before. We found the total current in the circuit. Now we need to know the voltage in each individual piece of the circuit. And because it's in series, this current has to be the current in the resistor, the capacitor, and the inductor. So, to find the voltage across the resistor, I'm going to use I times the resistance of the resistor. This is good old-fashioned Ohm's law stuff, right? So that's 0.0057 amps times 9,900 ohms gets me 56.43 volts. So the average or RMS voltage across that resistor is 56. All right? Voltage across the capacitor. I'm going to put in the current that I already know. And what am I going to put in for the resistance of the capacitor? X sub C. Right? Because that reactance, that capacitive reactance, is my resistance. So it's going to be 0.0057 times X sub C, which is 17,683. Again, it's amps times ohms gets you voltage, right? I got 101 volts. And then the inductor will be the current times the resistance of the inductor. 0.0057 times 9.425 gets me 0.054 volts. And so there I can see that the element in this circuit that is using up most of my electric potential is the capacitor, right? The inductor is hardly doing anything, and the resistor is doing whatever it is. All right. How do you check any of these problems? Granted, we don't understand where most of this math is coming from, right? But is there any quick check that we could do? So, this should be a voltage symbol. What did I do there? It's not X sub L. It's V sub L. All right. So, let's take a look at these voltages, right? Let me show you what not to do. Has anybody noticed a problem? If we add up all of these voltages, we get a number that's bigger than the voltage of the power supply to begin with, right? So either we just broke conservation of energy and the universe is going to implode, or something else is going on here. It's option B, by the way. So these are RMS values, right? These are like average values. Remember the simulation I showed you? Do the elements in these circuits, the resistor, the inductor, and the capacitor, do they wiggle at the same time in the same place? No, right? We're hiding the time-dependent parts of this circuit. And in hiding it, it seems like we kind of broke conservation of energy, but we didn't, okay? Just because that's the average voltage, that doesn't mean at any one instant in this circuit, that's what the voltage is for that thing, okay? At any one instant in this circuit, I can guarantee you that the total voltage across the resistor, inductor, and capacitor will be 115 volts. The capacitor could be negative voltage. The resistor could be positive voltage. The inductor could be, well, who cares? It's too small, right? Like they'll vary and be positive and negative, but no matter what happens, they will always add up to 115 volts in the instant that I go to measure. But because we're calculating these RMS values and ignoring the time dependence of these circuits, we can't really just look at these and go, oh, it didn't add up to 115. I must have screwed up. No, that doesn't work that way, right? So again, we're hiding a lot of things in the black box of impedance and these reactances that make it hard to check. And so really, the check for a lot of these things is check your math, right? But process is find the current, right? Okay, if you can find the current in your circuit, you can basically find out anything else you want about it. And it's really not going to be that hard because it's all going to be in series. Pretty sure I didn't do this to you, but like what happens if you have two inductors in series?
Multiply by 2.
Well, what if they're different? Just add them together, right? XL for 1, XL for 2, add them together, you've got the total resistance, right? Okay, so, yeah. And that's really kind of it for this chapter's like math parts, right? It's I don't know if it's if it's a letdown. Oh, it's not a letdown. I don't know. Maybe it's a little tiny breath of fresh air. It feels weird because like we're cheating and it's not really DC, but we're using DC and it's kind of different from DC. But like I said, accept it, go with the flow, try not to ask too many questions. If you start finding yourself wondering what a phasor is, stop, reevaluate your life's choices, and ignore phasors, okay? You just don't want to have to deal with a rotating vector, okay? All right, let's talk about like implications, like why AC is so good, right? And why we're forced to kind of acknowledge that it exists and try to tie this all back together with all the magnetism stuff that we have learned. I also want to kind of bring this back to something in 2A, which had to do with simple harmonic motion. Back in 2A, there was this concept and idea called resonance in a system that oscillates back and forth. I don't know what your teacher did back then. In my class, I always use the example of swinging on the swings as an example of resonance. Resonance is an increase in amplitude of a oscillation when you put energy into that oscillation at exactly the right time. When you're swinging on the swings, right? When is it that you like do the pull and the kick? You kind of as you're swinging backwards, right? And you're starting to turn around, that's when you do it. If you're pushing a kid on the swings, right? You're standing back here, they swing out, they come back, and then you push, right? It's not like you push here and then run over and push here, right? Okay? So in order for the amplitude of the swing to get bigger and bigger and bigger, you have to add the energy at the right time. And you can try this experiment. Go to the park, kick all the kids off the swings, you're bigger now, and then start like pump at random times. As random as you can make it, right? Human beings aren't so good at random, but like pump at like the bottom point. Be careful if you try to pump at the other end of the swing, you'll fall out. But like your amplitude will die. Okay, it'll just blah, 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 right? Because it just isn't, there's no resonance there. So why am I talking about this? In an AC circuit, we have basically swings going on, okay? The big kind of cheat with the power that comes out of the wall, right, is that no charge is being sent to you at all. In DC circuits, we're moving charges around, right? They get pumped by the battery, they go through the circuit, they deliver their energy, it's all done. But in AC circuits, what do the charges do? They just do this, right? Because the current goes that way and then it goes that way and it does it 120 times a second, right? Okay? So basically all we've got in the wires are vibrating electrons. So like how do we do any work with that? Okay? One of the ways that we can like capitalize on the fact that the electrons aren't going anywhere and we can deliver actual power through that wiggle is through this concept of resonance. I know this looks scary. Okay, it does look scary at first glance, okay? But in a circuit that consists of just an inductor and a capacitor, we're going to strip the resistance out because resistance is just like friction. It's like damped harmonic motion. We don't want to do the dampening coefficients, okay? If we take a fully charged capacitor, okay, such that all of the energy in the circuit is in this capacitor, okay? And then we let that capacitor, we connect it to an inductor. The capacitor will send current out, right? It'll try to, these positive charges want to be with these negative charges. And so they'll start flowing through the circuit, okay? So current happens. And as current happens, what happens when current flows through a solenoid or an inductor? Makes magnetic field, doesn't it? And so the energy that was in the capacitor, in the electric field of the capacitor, gets transferred into the magnetic field of the solenoid. But the solenoid, being a coil with magnetic field in it, and via Faraday's law and Lenz's law, is going to want to fight the changes in magnetic flux through it. As the capacitor discharges, it tries to slow down, right, the current. But now that the capacitor is fully discharged, and the inductor has all the magnetic field, it's going to start losing that magnetic field. And so Lenz's law says, no, I'm going to fight that. And so therefore I'm going to send current through the circuit so that we charge the capacitor again. Only notice it's charged backwards from what it was at the beginning, right? So now that the capacitor is fully charged and the inductor has stopped pushing because it has no more energy to push, what's the capacitor going to do? It's going to discharge, right? We have separation of positive and negatives. The capacitor wants to get those two charges to come back to each other, right? So current will flow. The solenoid will fight it and then try to keep it going such that it'll get back to this state. And now that our capacitor is fully charged, what's it going to do? It's going to discharge, and we're like back to the initial state. This circuit is just like a mass on a spring. A mass on a spring, when you displace it and let go, will bounce back and forth, right? Potential energy in the spring converted to kinetic energy, converted back into potential energy, then back to kinetic, and then potential, right? Back and forth, back and forth. What we have when we connect an inductor and a capacitor together is the electrical version of an oscillation. It's the electrical version of a kid on the swings. It's an electrical version of a mass on a spring. What can we do with an electrical circuit that ticks and talks? Tick, tock, tick, tock, tick, tock. What is this? It's a timing circuit, right? Like a pendulum clock. It's a timing circuit, okay? And so the frequency, the resonant frequency, the frequency that a circuit wants to tick-tock at, turns out to be 1 over 2 pi times the square root of L times C, okay? This is the magical frequency that if the circuit is convinced to oscillate at that frequency, we will get resonance, meaning that the current in the circuit will increase a lot. Okay? Just like a kid on the swings, when you push them, you don't have to push very hard. Each push can be very light, but over time, that kid will get swinging higher and higher and higher. Now, of course, given perfect, like no resistance or anything, we could get infinite amounts of current, but that's not what happens because there's resistance built into every natural system. So it peaks out after a while with resistance. This is the version without resistance in it. But I've got pictures of a car radio and a car antenna. Why are these here? We don't tune very many of our devices anymore, do we? Right? I mean, people don't listen to radio. You have music on your phone or whatever, right? Okay. But you actually every day tune, you don't, but your devices tune themselves constantly to various wireless signals that are out there. So I'm going to start with sort of the old-fashioned radio tuning, and then we're going to take this into cell phone territory, okay? This antenna on the car, how many radio stations is it picking up at the same time? All of them. Like it can't help but pick up every single radio station. It's just a thing of wire, right? And that thing of wire is capturing electromagnetic waves as they travel through the atmosphere. They've been released by some radio station, and the antenna is just like, I'm going to grab whatever wiggle I can find, right? So how does the radio in the car know which station you want to listen to? You tune it. That knob or the buttons are actually changing capacitance in a circuit. You don't change the inductance, you change the capacitance. So that dial is a capacitor, and as you twist it, you're changing the resonant frequency of the circuit. What frequency will be the most dominant from the ones that the antenna is picking up? It'll be the frequency that the circuit is tuned to. Back in the day, we used to drive along, and sometimes we'd hear two radio stations happening at the same time. It was really fun when rap and Christian tried to overlap at the same time, right? Okay, and so you'd hear both songs going at the same time. That's because they were both on the same frequency, but you were equidistant away from them, right? And so the circuit was like, okay, that's the frequency you want, that's the one I'm going to play, and you were getting both signals overlapping, right? So fast forward, okay, to modern day. Well, I loved this picture. I did a search for automobile antenna, and that one popped up. Wow. Anyway, okay, fast forward to modern day. Right? This is what a cell tower looks like, unless they look like those fake trees, which I always think look pretty funny. Right? Your phones have different antennas in them. What are all the different things that your phone can pick up? Like the different technologies or signals? Wi-Fi, Bluetooth. Cellular. Okay, so now that's 5G. LTE sometimes, right? 5G and LTE are different, frequencies. But then that's further broken down into data versus voice versus digital voice versus text. So your phone can actually pick up a lot of different frequencies, right? How does the phone know that a signal is Bluetooth versus Wi-Fi versus cellular? All the antennas in your phone have no choice. They have to pick up whatever wiggle is happening. Okay? But how do you tune the antenna? How do you tune the circuit? Resonance. These are AC things. The Wi-Fi coming out of that access point right now is coming as a wave in the electromagnetic spectrum, okay? The frequency of that wave depends on what, let's just pretend we're just attaching to slower, 2.4 gigahertz, okay? 5G is like 900 megahertz. There's different frequencies for these different things, right? But your phone, right, with the antennas in it, is able to figure out, is it Bluetooth, is it Wi-Fi, is it cellular, is it all these different things, based on the tuning of the different frequencies. And what's more, it gets way more complicated, to keep like the calls secure and to make sure that multiple people can be talking at the same time, your phone will do something called frequency hopping or spread spectrum hopping, where multiple thousands of times per second it will switch from one frequency to a different frequency. You may have heard of bandwidth. Bandwidth is a way of measuring how much information you can get through a frequency spectrum or a range of frequencies in a certain amount of time. The person who's responsible for figuring out this technology that allows all of us to talk wirelessly, her name was Hedy Lamarr. And she, if you think you know that name, it's because she was an actress in Hollywood in the 1930s and 40s. She was an Austrian immigrant. She had fled Austria in the late 20s, seeing the rise of fascism. And she came, and she was very glamorous, and that classic movie star look and all that kind of stuff. But between takes in her dressing room, she was developing all of the electromagnetic science and engineering that would later become what we use in cell phones. They initially used it in World War II to try to keep the Axis powers from being able to listen in on radio communications. But she was the one that developed our modern understanding of how all of this works, right? So go watch a Hedy Lamarr movie and then thank her for being able to walk around with the world's combined knowledge in our pockets. I actually don't think this is a real quiz. Yeah, because it's numb. That was just a placeholder slide. I did that whole thing in less than a class period. So I'll let you guys go early, right? Don't thank me. You guys have to deal with the homework still. What are we going to do on Monday? Review. Yeah, Monday's review for the exam, right? So come on in. We can get home. You're going to have 3 hours, right? So plenty of time to ask questions, button up the homework, all that kind of stuff. If I don't see you in grasp, I'll see you Monday.